So, welcome everyone to the continuations. Our second speaker is Fiona Seibold, and she will talk about integrable deformations of superstrings. So, please, the floor is yours.
Thank you. So first of all, thanks to the organizers for putting together this nice conference and giving me the opportunity to give a talk. So as advertised in the title, my talk will be about integrable deformations of superstrings. And I will try to give more of an introduction to integrable superstrings and integrable deformations. But if you're looking for references, this talk is mainly based on a paper of 2018 with Ben Hoare and also two other papers with Stijn van Tongeren and Yannick Zimmerman. So let's start by giving some motivation why I want to study these integrable deformations. So in the previous talk, Bob introduced the ADS-CFT correspondence, so the duality between strings on ADS space and the unconformal field theories living in one dimension less. And he was looking at one specific example where you could actually do computations. And this is really a recurrent theme in this ADS-CFT correspondence is to actually do explicit calculations. And one property that will allow you to do such computations is the property of integrability. And this was discovered in the early 2000s that type 2b, this ADS5 process 5 superstring in the free string limit, and also n equal 4 super Young Mills in the planar graph limit has this property of integrability. And integrability, so there are many tools that have been developed. So there is a whole integrability package that has been developed in order to actually compute observables on both sides. So for instance, the string spectrum, and also that is drawn to the anomalous dimension of operators. And there is also progress that is made in using integrability to compute higher point correlation functions. And the question that you can then ask is whether there are other superstring theories for which the integrability program can be applied. So to go beyond the ADS5 process 5 superstring. And well, now that you have heard the previous talk, you already know the answer. Namely, you can always go to, so the answer is yes, and you can always go to lower dimensional ADS-CFT setup. So Bob was talking about ADS3 cross S3 cross T4, but there are also other string theories that are imported in this correspondence. So for instance, ADS2 cross S2 cross T6, or also ADS4 cross CP3, for instance. So in this, for these lower dimensional ADS-CFT setups, you have less supersymmetries than for ADS5 process 5. And there are also new features that appear, and therefore these are also very interesting to study on their own. However, they are still the most supersymmetric in their respective dimensions. And you might want to go beyond that. And a way to go beyond that is to consider integrable deformations. So depending exactly on your research, you might have already come across integrable deformations, just not, you didn't put the name on them. So for instance, a type of integrable deformation are TST transformations. So this you can apply whenever you have two isometries, and then you do a combination of T duality in one isometry, then you do a shift. So you shift one isometry with the other isometry, and then you T-dualize back. And so this type of transformation will map you from a given string theory to another string theory. And in some cases, the dual is known. So this is, for instance, the case if you do a TST transformation on the two isometries of the 5 sphere. So you arrive at the Lie-Strasser deformation, and this is dual to the beta deformation of n equal 4 super Young Mills. So there are other types of integrable deformations that you can do. So namely, so here I will just give the names, and depending on exactly what your research is, you might already have come across these names. So TT bar deformations, or more general current deformations. You can also do quantum deformations, in particular eta deformations, or also lambda deformations, or more general Young-Baxter deformations. So in this talk, I will focus on one specific type of integrable deformation, namely eta deformations. And I will ask two questions. One question is, what is the interpretation of eta deformations in the context of string theory? So in the case of TST transformations, I told you that by doing this deformation, you stay within the realm of string theories. However, when you do eta deformations, there is nothing that guarantees you that after doing the after deformation, your theory that you end up with is still a string theory. So this is one point that we will analyze. Another point that I will address is the scattering theory of eta deform models. And this is an interesting point to look at, because these powerful integrability techniques that I mentioned that will allow you to actually look at the string spectrum, for instance, all these methods are based on the scattering theory, the worldsheet S matrix of these theories. So it's very important to actually find this S matrix. So those are the two questions that I want to answer during the talk. And if you have urgent questions, please don't hesitate to just interrupt me. So this is the plan of the talk. So first of all, I've been talking now about integrability and integrability in ADS 5 cross S5, but perhaps you have never come across these notions. So I will just give you some notions of classical integrability. And then I will actually show you how these eta deformations are defined. So what is their action? And then we will look at the deformed, at their interpretation in the context of string theory, and look at the scattering theory of the deformed models. And we will end with some conclusions, and also I will give an outlook of open questions that still remain to be answered. So let's start with some notions of classical integrability. So loosely speaking, a theory is called integrable when there are enough conserved charges so that you can, so these conserved charges will constrain the dynamics of your theory so much that you will be able to solve the equations of motion. So in Hamiltonian mechanics, it's possible to make this definition a bit more precise, and this is the concept of Liouville integrability. So if you have a Hamiltonian system with n degrees of freedom, then this is called Liouville integrable if you also can find n independent conserved quantities that are in involution. And by involution, I mean that the Poisson bracket gives zero. The Poisson bracket gives zero. And if this is the case, then the theory is called Liouville integrable, and you can solve it by quadrature, meaning that you can express the solution to the equations of motion as a direct integration. There exists also a more modern approach to integrability, which is the Lax formulation of integrability. Namely, if you can rewrite the equations of motion in terms of this specific equation for L and M, which are square matrices whose entries are functions of the space-based variables, then the theory is integrable, and you can construct a tower of conserved charges by considering the trace of powers of this matrix L. And if you manage to show that these conserved quantities are independent and in involution, then you go back to the concept of Liouville integrability that I introduced previously. So the reason why I introduced the Lax formulation of integrability is that this will become important in the context of field theories. So field theories, they have infinitely many degrees of freedom, and the Liouville integrability that I mentioned, there you really made the assumption that you have this capital N, the number of degrees of freedom, that is finite. So this definition you can no longer apply in the context of field theories because you have an infinite many degrees of freedom. However, the Lax formulation of integrability that I introduced, this one you can readily apply to the case of two-dimensional field theories. So for two-dimensional field theories, if you can recast the equations of motion as a flatness condition for this lax connection curly L, then you call your theory integrable, and similarly to the one-dimensional case, there is a prescription on how to construct a tower of conserved charges. And I don't want to go into detail, but this is through the monodromy matrix. So therefore, we have a good definition of classical integrability for two-dimensional field theories. And this will become very important in the context of string theory, because you can actually think of string theory as a special type of two-dimensional field theory, where, so it's a theory for fields x mu that are mapped from the two-dimensional world sheet to a time-dimensional target space. So the fact that it is a two-dimensional field theory is hidden in the fact that the world sheet is two-dimensional. And this two-dimensional, this 10-dimensional target space is the space-time. And in the context of superstring theory, so if you have taken a course in superstring theory, you know that there are constraints on this target space, namely it should be 10-dimensional, and it should also solve the supergravity equations of motion. So for instance, a type of target space, and for some target spaces, the theory will become integrable. And this is the case, for instance, for ADS5 cross S5. So when the target space is given by the product of a 5-dimensional anti-de Sitter space times a 5-dimensional sphere. And since you consider actually a superstring, you also have like other structures, and these are the Ramo-Ramo fluxes. And here ADS5 cross S5 is supported by a 5-form Ramo-Ramo flux, and this will be such that the full background solves the supergravity equations of motion. And integrability can be traced back to the symmetries of this space-time, so of ADS5 cross S5. So let's look more closely at the symmetries of this background. So you have ADS5, that is a symmetric space, namely you can write it as a coset of Lie groups. And also S5 is a symmetric space. And if you add supersymmetry to the setup, then you end up with what is called a semi-symmetric space. So the quotient of a Lie supergroup over a Lie group. And integrability, so classical integrability, then follows from the formulation of the Green-Schwarz superstring as a sigma model on a semi-symmetric space. And the deformation that I will consider later will be deformations of this semi-symmetric space sigma model. So before defining the deformation, let me first define the model, actually, the semi-symmetric space sigma model. So the semi-symmetric space sigma model is a sigma model on a semi-symmetric space. So namely the quotient of a Lie supergroup by a Lie group, where the Lie supergroup has a Lie algebra with Z4 grading. So you have G0 and G2 that are the elements with even grading. So this in physical term would be your bosonic generators. And then you have G1 and G3 that are your elements with odd grading. So these would be your fermionic generators. The Z4 grading is compatible with the commutator, and G0 forms a subalgebra that is identified with the Lie algebra of the Lie group H. In order to define the action of the ADS5 cross S5 superstring or of the semi-symmetric space sigma model, I will need to introduce Pi, which are projectors onto the spaces Gi, and I will also call the added variant bilinear form on G by the supertrace, just because when you work in terms of a matrix realization, this in general is the supertrace. So this is the action of the semi-symmetric space sigma model. So what are the different ingredients? You have an overall constant, which is the string tension T, Then you have the integration over the two-dimensional worldsheet coordinates tau and sigma. You have gamma ij, which is the Weyl invariant metric on the worldsheet, and you have epsilon ij, the antisymmetric tensor. And then the rest of the action is constructed out of the left invariant Marek-Cartan forms G inverse dg, and you also have a projector here. So G is a supergroup valued field, and yes, the supergroup valued field, and this projector will be such that you have a local right-acting gauge symmetry. G goes to GH, where H belongs to the Lie group H, capital H. And because the theory is constructed out of the left invariant Marek-Cartan forms, it has a global left-acting G symmetry that acts in this way. And so maybe a comment about this projector that you need to insert. Here, this factor of 1/2 is fixed by the requirement of kappa symmetry. So this is just something that you need to ensure so that you have the same number of fermionic degrees of freedom and bosonic degrees of freedom as expected in supersymmetry. And yeah, the bottom line of all this is that this action is classically integrable in the sense that you can recast the equations of motion arising from this action in terms of the flatness condition of a lax connection. And depending on the choice of capital G and capital H, you will be able to describe superstrings moving on various ADS backgrounds. So for instance, in the case of ADS 5 cross S5, I've already told you that the symmetries are is given by this quotient PSU2,2/4 by SO1,4 times SO5. But you can also describe other string theories. In particular, you can also describe ADS2 cross S2 cross D6 or ADS3 cross S3 cross D4, which are also have this property of classical integrability. So now that we have defined the original undeformed theory, this semisymmetric space sigma model, let us look at the deformed theories. So I will now introduce the integrable eta deformations. So the crucial ingredient of the eta deformations are what is called a Drinfeld-Jimbo operator, R. So this is a linear map from the G into G. So I recall that G is the symmetry algebra of the undeformed theory. And it acts as follows. So its action is actually defined by the choice of a Cartan-Weyl basis of G. So you decompose your G into Cartan elements H, into positive roots E plus and negative roots E minus. And then this Drinfeld-Jimbo operator, it will annihilate the Cartan elements and multiply with plus and minus I the positive and negative roots. Other important properties of this Drinfeld-Jimbo operator are that it is antisymmetric with respect to the supertrace, and it also satisfies what is called the inhomogeneous classical Yang-Baxter equation. So this equation here. So this is the ingredient of this eta deformation. And now let's see how this ingredient is used in order to define the action. So this is the action of the eta deformed model. So you see that it is similar to the undeformed semisymmetric space sigma model, except that you have now this non-trivial operator here appearing. And you have two new ingredients. So this parameter eta that gives the name to the model. So this is a real parameter, and eta equal to 0 actually gives you back the undeformed model. And again, you have this operator R that appears here in the denominator of this operator here. you also have to change slightly the projectors. So let's look at the properties of the deformed action. So previously we had this global left acting symmetry. And if you deform the theory, you will no longer have this global left acting symmetry. It will be broken to a bunch of U1s. However, you still have the local right acting symmetry. You also preserve kappa symmetry, and this operator R and the action have been chosen precisely such that you retain the classical integrability of the model. So again, you can rewrite the equations of motion in terms of the flatness condition of a lax connection. So this is the action of the eta deformed model. But before, I also told you that the integrability of the ADS 5x5 superstring can be traced back to the symmetries of the model. And here I told you that the eta deformation actually breaks these symmetries. So why is it that this deformed model is still integrable? And the reason is that there is actually a hidden quantum group symmetry. And so if you have followed already the conference yesterday, then you have already encountered these quantum groups. And this was in the first talk of yesterday by Nejla. So she wrote it UQ of G. But I will recall some important properties of these quantum groups here. So let's start with the Lie algebra G, that again I decompose into Cartan elements and positive and negative roots. Then the commutation relations are fixed by the Cartan matrix, and you can actually promote this to a Hopf algebra by adding a new operation that is the coproduct denoted by this delta, which is a Lie algebra homomorphism. Yes, and in order to define the quantum group, you modify slightly you modify the commutation relations. In particular, you modify the commutation relations involving positive and negative roots. So instead of having on the right-hand side just the Cartan element H, you now have Q to the H. So you have a parameter Q. And again, you can promote this. So this is a Hopf algebra with this. You also need to modify the coproduct. You have now, instead of the identity for the positive and negative roots here, you have insertion of Q to the H. So all this was already in Nejla's talk yesterday. And if you take Q, so this is like a one parameter deformation of your algebra. And if you take Q going to 1, then you recover the original undeformed algebra. And something that I want to point out, because it will be actually important for the rest of the talk, is that there is a subtlety in the case of Q deformations or quantum groups of for quantum supergroups, like for in the case you consider deformations of a Lie superalgebra, not an ordinary Lie algebra. And this has to do with the fact that in this case, so for Lie superalgebras, you can choose different Cartan Weyl bases, so you can do this decomposition in different ways, and the quantum groups that you then construct using this decomposition will actually be different. And in order to highlight this, I will use a specific example of a supergroup or a superalgebra, so namely SL2/2, which is kind of the minimal example. So let's consider SL2/2. So you can think of that as being the set of 4x4 matrices with vanishing supertrace, and the 2x2 diagonal blocks here in blue are the bosonic generators, and the 2x2 out of diagonal blocks are the fermionic generators. Now, when you work in terms of a matrix realization, it is customary to take the Cartan elements to lie on the diagonal and have the positive roots to be in the upper triangular part of the matrix and the negative roots that are in the lower triangular part of the matrix. And this actually corresponds to the choice of simple roots that are here highlighted with this white circle. So the simple roots are just above the diagonal, the simple positive roots. So this is the associated Cartan matrix, and this is the associated thinking diagram. And here the empty circle denotes a positive simple root, and a circle with a cross denotes a fermionic simple root. So this is one type of thinking diagram for SL2/2, but in fact there are two more. So here I wrote down their Cartan matrices and the thinking diagram. So you see that you have an increasing number of fermionic simple roots. And so let's now see what happens if you choose two Cartan whale. So if you, in order to build your quantum group, you use Cartan whale bases that are associated to two different thinking diagrams. So let's look at the quantum deformation built out of one Cartan whale basis and the quantum deformation built of using another Cartan whale basis with different thinking diagram. Then what happens is that the Q-deformed algebras, they are isomorphic, but the Q-deformed, the coproducts are related by a twist. So they are no longer the same. In particular, for our example of SL2/2 with the distinguished thinking diagram, so this thinking diagram with two bosonic simple roots and one fermionic simple root, and this fermionic thinking diagram where all three simple roots are fermionic, then this twist, it involves the fermionic simple root in the middle, and it reads like this. And then when you take Q going to 1, you see that you just recover the identity. So this is how this different choice of Cartan whale basis affects the quantum groups. And you can now actually also see that at the level of the action, namely this Drinfeld-Gimpo operator. Again, it was defined in terms by choosing a Cartan whale basis. And if you choose two different Cartan whale, so if you choose Cartan whale bases that are associated to two different thinking diagrams, then you cannot reabsorb the change into a field redefinition, and therefore you really end up with two different models. So the bottom line of all this is that eta deformations are not defined uniquely. They are kind of classified by the thinking diagrams of the Lie superalgebra of your undeformed theory, and this will have an impact on the interpretation as a string theory and also on the scattering theory of the models. So let's now look at the interpretation of these different eta deformations in string theory. So these eta deformations, they will deform the space-time in which the strings propagate. So if you start with ADS5 cross S5, you do the eta deformation of ADS5 cross S5. The geometry that you end up is no longer ADS5 cross S5, but it is a one parameter deformation of the original geometry. So for instance, here I have illustrated how the deformation affects, for instance, the sphere. So when eta equal to 0, so this is the undeformed background, then you get just a sphere. And then once you turn on the deformation, so if eta becomes now non-zero, you will squash the sphere. And similarly also for ADS, you will have a deformation. And in fact, also the also the fluxes that are supporting the bosonic geometry, they are also modified. So here I put a upper script R to highlight the fact that the deformation will really, the background that you obtain will really depend on the Dreamfield Jimbo R matrix that you use. So the different eta deformations will have different backgrounds. And an important question to ask is then whether the deformed theories can be interpreted as string theories, because in string theory, the background should satisfy the supergravity equations of motion. So we should ask whether also the deformed backgrounds will do so. And I will approach this question maybe in a more historical way, and with the paper of 2015 by Arutunov, Borsato, and Frolov, where they looked at one particular eta deformation that I will call the ABF deformation or ABF background, according to the initials of the authors of this paper. So it's important to keep in mind that this is associated to one type of Dreamfield-Jimbo operator R. So they looked at this background and they found that it actually does not satisfy the supergravity equations of motion. And this was a bit of a puzzle at the time. But now we know that there are actually different types of eta deformations, and we know that we should also look at these other types of eta deformations to see whether there we could find something that solves the supergravity equations of motion. So this ABF eta deformation was using an operator R that was based on the distinguished thinking diagram of the symmetry algebra PSU2,2/4. And yeah, again, this when you work in terms of matrices, this is kind of a natural thing to use, because this is when the simple roots are just above the diagonal. However, there are many more eta deformations, because PSU2,2/4 admits many more thinking diagrams. I've listed a few here. And we should actually study the deformed backgrounds for all these data deformations based on these different, using these different thinking diagrams. And it turns out that the different eta deformations, they will have the same metric and B field, but the Ramon fluxes that support this bosonic geometry will be actually different. And in order for the background to be a supergravity solution, so for the background to solve the supergravity equations of motion, the operator R, the Dreamfield-Jimbo operator that is used to construct the eta deformation, should satisfy a special condition, which is called unimodularity condition. And if you look at all the types of thinking diagrams, then you actually find that only operators R that are associated to the fully fermionic thinking diagram, so using Cartan-Weyl basis with fully fermionic thinking diagram, then only those are unimodular. And you can, for this special case, so you can construct the background explicitly, and indeed the supergravity equations of motion have been checked. So indeed it is a supergravity solution. So the other eta deformations that are based on the other types of thinking diagrams, they do not solve the supergravity equations of motion, but they are very closely related to theories that do solve the supergravity equations of motions. And this is something that I will not go into more details here, but if you have questions at the end of the talk or in the discussion, then you can ask. But these different eta deform backgrounds, so they all solve a set of generalized supergravity equations of motion that actually can be traced back to the kappa symmetry of these models. But as I said, I will not go into more details of what these generalized supergravity equations of motions are. Instead, I will jump directly to the last part of the talk, in which I will discuss the scattering theory of the deformed models. So you might want to understand what types of constraints integrability imposes on two-dimensional quantum field theories. And for quantum field theories, you expect the system to be integrable if the underlying classical theory is integrable, and also if the conserved charges survive quantization. And this will actually impose serious constraints on the scattering matrix of the theory. And we have already encountered some constraints in previous talks, but I will again repeat maybe these constraints here. So one constraint is that you cannot have any particle production. The second constraint is that the set of incoming momenta is the same as the set of outgoing momenta. And then you also have the property of factorization. So if you have an n-body scattering event, you can factorize it into the product of two-body scattering events. And this factorization condition will actually impose constraints on the two-body S matrix. And this you can see by looking at the scattering of three particles. So 1, 2, and 3. And the scattering can be done in two different ways. So you can scatter particles 1 and 2 first, or particle 2 and 3 first. And requiring that this gives the same result will impose a constraint on the two-body S matrix, which is called the quantum Yang-Baxter equation. So for your quantum theory to be integrable, the S matrix should solve the quantum Yang-Baxter equation. So how do you actually proceed in order to obtain the S matrix? So first, I need to tell you that the S matrix that I consider is really the worldsheet S matrix, so the S matrix of excitations on the worldsheet. And in order to actually have well-defined asymptotic states, I need to go to the decompactification limit, where I take where this worldsheet becomes flat. And I also need to fix some redundancies in my theory by fixing light cone gauge. And this will allow me to arrive at a massive two-dimensional field theory for which I can compute the worldsheet S matrix. So you can compute this S matrix perturbatively. So you will have this worldsheet S matrix will be given by the identity, and then you have the three-level contribution, the one-loop contribution, as Bob mentioned in his talk. But in integrability, you can also use you can also obtain the exact S matrix, so the all-loop S matrix, using the symmetries of the theory. So you really use the symmetries of the theory in order to obtain the exact S matrix. And then, of course, in order to be sure that you are doing the right thing, you should expand this exact S matrix and check against the perturbative calculations. And this exact S matrix for an integrable theory should satisfy the quantum Yang-Baxter equation. And the reason why this S matrix is very important, this exact S matrix, is that the integrability techniques to find the string spectrum, they really use this S matrix. So it's really at the heart of the integrability techniques. So let's look now at the case of ADS5 cross S5. So as I told you, the exact S matrix is constrained by the symmetry of the theory. So here it's really the quantum theory that you should consider. So in the case of the ADS5 cross S5 superstring, you started with PSU2, 2/4. But when you go to the quantum theory, so also when you do this light cone gauge fixing, you end up with 2 copies of SU2/2 centrally extended. So this is the symmetry that you need to consider in order to constrain the S matrix. Now, in the case of the eta deformed ADS5 cross S5, you start with the Q deformation of PSU 2,2/4, and the symmetry algebra that you need to consider is again, so here you again have Q deformations of the different SU2/2 factors. So I told you that you have these different eta deformations depending on which Dinkin diagram you choose in order to construct the model, and also for the quantum for this Lie algebra A, you will have different Dinkin diagrams. So you have to understand how the symmetry breaking pattern works. So which Dinkin diagram is mapped to which Dinkin diagram. And so let's do this analysis for these two extremal cases, the distinguished Dinkin diagram and the fermionic Dinkin diagram. So in the case of the distinguished Dinkin diagram, the symmetry breaking pattern is the following. So you have the distinguished Dinkin diagram of PSU 2,2/4, and you also need to consider the Q deformation SU2/2 that is based again on the distinguished Dinkin diagram of SU2/2. And similar also for the fermionic Dinkin diagram, let's analyze the symmetry breaking pattern, and it is the following. And in both cases, you can use the symmetries, so this SUQ2/2 plus SU1/Q2/2 in order to construct the exact Q deformed S matrix, and you can show that in both cases it solves the quantum Yang-Baxter equation. And furthermore, I mean, you need to check that indeed what you're doing makes sense, and the expansion should match the corresponding perturbative S matrix, and this is indeed the case. Furthermore, these two different algebras, at some point I told you that their coproduct is related by a twist. And in fact, this twist will also appear at the level of the S matrices. So if I denote by S, the S matrix associated with the for the eta deformation based on the distinguished Dinkin diagram, and the S prime, the S matrix for the eta deformation based on the fully fermionic Dinkin diagram, then the two S matrices are related in this way, where F is the twist that allows you to go from this Dinkin diagram to this one at the level of the coproduct.
So sorry, just want to say that you still have a couple of minutes left. So.
Okay. Well, I now come to the conclusions. So what did we actually learn here? So we learned that a way to generate new integrable theories is to actually start from your known integrable theory and deform it in such a way as to preserve integrability. And this is the concept of integrable deformations. And a particular example of integrable deformation are these eta deformations that correspond to a Q deformation of the symmetry algebra. And the important aspect that we have seen is that eta deformations of superstrings, or similarly Q deformations of superalgebras, they are not unique. They will actually depend on the Cartan-Weyl basis that you choose in order to construct this Drimfeld-Jimbo R matrix to define the action of the eta deformation, or similarly, it will depend on the Cartan-Weyl basis that you use in order to build the Q deformation. And we have analyzed the status of these eta deformations in the context of string theory, and we found that only the eta deformations that are constructed using Drimfeld-Jimbo operators that are associated to fully fermionic Dinkin diagrams solve the supergravity equations of motion, and therefore have a direct interpretation in terms of string theory. We also looked at the scattering a theory of the deformed model, and we have seen that the different S matrices are related by a twist, and we also checked that there is a matching between the exact Q-deformed S matrix that is built using the symmetries of the model and the perturbative S matrix. So this is a good check that you indeed have this Q-deformed symmetry. And maybe one thing that I want to mention is that in this talk, I focused on ADS5 x S5, just for the sake of taking an example, but this actually holds. You can also look at other cases, for instance, ADS3 x S3 x T4, and there you actually see the same type of pattern, namely, again, you have a supergravity solution if you take fully fermionic thinking diagrams. And so in the case of the S matrix, it's a bit more subtle because there the Lie algebra is so small that you actually have only one thinking diagram, and therefore all the different eta deformations have the same S matrix. But just to mention that you can also apply this to lower dimensional ADS CFT setups. And let's see some open problems. So first, the S matrices are related by a twist for these different eta deformations. But maybe it would be also good to understand this twist at the level of the background. So if it's possible to go from one eta deformed background to the other eta deformed background by some type of generalized duality, so not an ordinary T-duality, but some generalized T-duality. And also an important point is to understand this twist, how this twist affects the physical observables. So I told you that the S matrix is used to compute the spectrum of the theory. So how does this twist that appears at the level of the S matrix impact the spectrum? And a part is also to understand better the Weil anomaly in these eta deformations. So why some eta deformations do not solve the supergravity equations of motion, and also whether they could still be understood as string theories in some sense. And another point is the connection between eta and lambda deformations. So eta deformations have been the subject of this talk, and they are quantum deformations with this parameter Q that is real. Lambda deformations, they are also quantum deformations, but with Q being a root of unity. And these two different models are actually related by Poisson-Lie duality. And it would be interesting to see whether these different eta deformations are related to different lambda deformations or the same lambda deformation. So this is also an open question. And last, but this is more like a general question, is how you can think of these Q deformations in the context of holography. So now that you have deformed the ADS part of the duality, so this the strings, whether you still have some kind of duality with some deformed CFT. So that's all what I wanted to say, and I thank you for your attention. And please don't hesitate to ask questions.
Thank you very much for a very nice talk. So let's thank Fiona for the presentation. Yeah. So, and please, questions. Yeah, Corina. You have to answer. You have to unmute yourself. I don't. We might have lost Corina. Does anyone hear Corina? No, right?
No, I didn't.
No. Wait.
Now it works.
You can hear me now?
Yes.
Okay, I don't know what happened. So yeah, it's actually, it might be a naive question, but I mean, how can I think of this twist? So, I mean, for me, I know like twists of Hopf algebras, So they come from, like, those are 2 cycles for Hopf algebras. Is here like a twist also some kind of 2 co-cycle, but for super Hopf algebras? Or
so I'm not.
How do you find? Yeah.
I'm not very familiar with the notion of 2 co-cycle, so
or maybe let me ask it differently. So, I mean, do you have some equation for this twist that's coming from the, like, an equation?
Yes, exactly.
The co-product?
Yes, exactly.
Okay.
There is such an so I guess it is exactly this equation that you are mentioning. Yes.
Okay, but just for super Hopf algebras, and so
yes.
here you okay. And is there a method to solve this? Like, how do you find like expressions for this twist?
Okay. So so these different thinking diagrams that I mentioned, you can actually go from one to the other by so-called generalized Wald transformations. So you take a fermionic simple root and then you change the nature of the 2 adjacent nodes. Like if you have bosonic, fermionic, bosonic, then you do a Wald transformation, generalized Wald transformation in the middle fermionic simple root, and this will give you the thinking diagram fermionic, fermionic, fermionic. And there is actually a formula then for what the twist is, namely it's precisely what I showed you. Is it involves this root on which you do the generalized Wald transformation. Okay.
Friedrich, we don't hear you.
Thank you. Yes, so I was just saying that Ondra has a question and now I unmuted him.
Hi. You mentioned that you also deformed the RR fields, right? Not only the B and G, but where do you read that from? Because in WZW model they do not enter, right? Or like the G and B enters explicitly, and I can read off what the new one is.
So okay. So several things. So one thing is that in my case, this is not a Westum-Minovita model. Second thing is that actually you can make it so that the metric and B field are the same and only the Ramon-Ramon fluxes are modified. And the way you actually find these Ramon-Ramon fluxes is that I showed you, yeah, just look at this action, and there is also, this should be, so this is the deformation of the semi-symmetric space sigma model, but it should also be equal to just a Green-Schwarz string that unfortunately I don't have the action here, but this Green-Schwarz string you can expand in fermions and it has a specific form, and from comparing these 2 actions you can read out the metric, the B field, and the fluxes.
Right. So do I understand correctly that big chunk between G inverse DG, those 2 guys, there's just information about B, G, and F all included. You just
exactly.
need to read it off. Okay.
So in this, yeah.
I
so
see.
the information about the metric and B field and Ramon-Ramon fluxes is included in this thing here.
I see. Gotcha. Thank you. Yeah.
And then if you do the expansion in fermions, then you can match it with the Green-Schwarz string, and this really gives you the metric B field and Ramon-Ramon fluxes.
Right. Thank you.
Very good. I have a brief question. So you said that for these different eta deformations, this universal sector stays the same, and you are changing the RR part. So right. So in the ADS 5 crosses 5, there is only the 5 form flux there, right? The others are not there.
So first, it might be a bit sloppy to say that the metric and B field are the same, because I mean, for instance, for ADS 5, the Lie algebra is SU2/2, and you can take different real forms, and depending on the different real forms that you take, you actually obtain different metrics, but you can have go from one to the other by a map. So yeah, The second, sorry, now I
Yes,
don't
so
remember.
yeah, I just wanted to ask that if when you deform, if it still stays the same, that there is only the 5 form flux, or you
Good, yes. So for ADS5 process 5, there is only the 5 form flux. In the case of eta deformed ADS5 process 5, you have the other ones are also turned on. And if I remember correctly, you have 3 form flux, 5 form flux. I think the 1 form flux, well, it depends on the eta deformation that you consider, but you turn on the other ones, yes.
I see. Okay, thank you. Okay, any other questions? Okay, then if not, then let's thank Fiona again for a very nice talk. So.
Thanks.